would like to now introduce you to our presenter today. We have Bill Evans, and he is the Senior Product Manager at WD. We also have Britton Spagnola on the line to make sure all of your questions get answered, so be sure to put those in anytime during the presentation. And she is the Senior Programs Manager for WD. So Bill, whenever you're ready, take it away.
Thanks, Abby. Good morning, everybody. My name is Bill Evans, and I am an employee of WD Corporation based in our offices in beautiful Mountain View, California. This morning I want to share with you some insights about the role that deduplication plays in network backup and what you should know to take advantage of Dedupe technology. But before I begin, I want to remind you that not only is Western Digital the world's largest manufacturer of hard disk drives and a major provider of consumer direct attach storage and NAS, we also have a line of products for small and medium businesses. These products for small and medium businesses include network attached storage, the WD Sentinel line of products, and network backup appliances and software. That's our WD Arkeia line. WD expanded into network backup products for SMBs with the acquisition of Arkeia software at the end of last year. So in the time we have this morning, I want to share with you some insight into data deduplication. I'm sure many of you are already familiar with deduplication, but I want to give you a quick review on deduplication versus compression, why dedupe is important for backup, how you can deploy deduplication differently in backup, whether target side or source side, strategies for block decomposition, benefits of application-aware dedupe, and then a comparison of the techniques known as fixed, variable, and progressive deduplication. The more you know, the more effectively you can make decisions, good business decisions in your company's favor. First, let me emphasize that deduplication is a kind of compression. We say at WD that there are two kinds of compression. There's local compression and global compression. Local compression is the type that most people are familiar with. Most local compression algorithms are specific to certain data types. Some of the best known are JPEG and MPEG, designed for images and videos. A more general algorithm for compression is the deflate algorithm. That's the most commonly used algorithm in the zip application. Global compression, by comparison, is used not on files or blocks, but on bigger things, file systems as an example. And one example of a technology used to compress file systems is deduplication. Another is byte differencing. Today we'll focus on deduplication. So in the beginning, deduplication was known as single instance storage. This is file grain deduplication. Today, most deduplication, whether of files for storage or of files and data streams for backup, is used at a block grain. So rather than calculating a hash for an entire file and comparing it to the hashes of known files, block grain deduplication takes a file and divides it into components. The components of a file can be moved to target storage, but if two files reference the same component, only a pointer to that component has to be written. So this block grain deduplication can dramatically reduce the volume of storage needed to store a set of files. This example shows 4 files, each of the files containing blocks common to the others. Note that the compression is done before the block is pushed to the target storage. The role of deduplication is especially important for backup. Everybody knows that deduplication reduces storage volumes. You saw that on the previous slide. But deduplication is especially important for backup because not only does it benefit from the reduction in storage required, but it will also shorten your backup window because less data has to be moved over the network. In addition, deduplication is especially effective when used for backup. For any general application of deduplication, you get benefits if you have many files of the same type. Say, for example, you have multiple PowerPoint files, and multiple files might contain different versions of the same PowerPoint presentation. This is great fodder for deduplication because block grain deduplication can identify the parts of the file that are in common with other files. So having lots of files of the same type is great. Similarly, having lots of computers that you're backing up, that is, for global deduplication, having lots of computers is great because very often the same files or the same parts of files exist on many different computers. These are benefits you get in almost any application of deduplication. But what makes backup benefit particularly from dedupe is the time dimension. In addition to the computer dimension and the file dimension, there's the time dimension. So that if you back up a file today and then you back up the same file again tomorrow, chances are most of the content in those two backups is going to be the same. The classic case is an outlook.pst file. These files are generally very, very large, but change very little from one day to the next. So by using block grain deduplication, you can hugely reduce the amount of storage necessary to back up your outlook.pst file on a daily basis. Now, relevant to backup is the concept of doing deduplication at the source versus doing deduplication at the target. Target deduplication means you're doing the deduplication operation. You're compressing the data either at the media server or at the backup server. So you get the benefit of reduced volume, but you still suffer from the need to move the entire file before compression over the network. You can see that the file is first moved over the network and then compressed. By comparison, if you look at source-side deduplication, the compression is done at the source before it's moved over the network. So here, the files would be compressed, would be deduplicated, and then only unique blocks would be pushed over the network. This greatly reduces the amount of network bandwidth you need to run your backups and therefore makes your backups faster. This increase in performance for backups is the primary benefit of deduplication when it comes to backups. These two approaches, target and source deduplication, also represent two different mechanisms, two different philosophies for scaling a backup server. When all of the deduplication is done on the backup server, to back up larger numbers of machines in less and less time, you need a more powerful backup server and you need a faster network. This is a scale-up solution. By comparison, if you're doing deduplication at the source, you have a scale-out solution because each of the data sources, each of those computers, is doing the deduplication using its own CPU and memory before sending the new blocks, the unique blocks, over the network. This is a scale-out solution and is well understood to be better from a cost perspective and a performance perspective. Now, block grain deduplication is really pretty simple. It consists of simply two steps. The first step is to take your file or your data source and divide it into blocks. There are several recipes for dividing a file into blocks. The three most popular are shown here. The first is fixed block. In fixed block, you have multiple blocks that compose a file. and these blocks are non-overlapping and of fixed size. Sometimes people refer to these blocks as chunks or subfiles, but they're clearly all simply parts of the file, generally smaller than the file itself. The second strategy for decomposing a file into blocks is called the variable block dedupe strategy. Here you have non-overlapping blocks, but they can be of different sizes. This takes a little bit more CPU, so it's a little bit slower, but the compression ratios are generally higher for reasons we'll see later in this presentation. The third approach, called progressive deduplication, is like fixed block because it has only a single size block, but it's different because the blocks can overlap. This is non-intuitive. It's non-intuitive because you wouldn't think that you would want overlapping blocks if your objective was to compress a file. We'll learn more about this later. The second step in any block grain dedupe operation is to calculate a fingerprint of a particular block. Each block has a unique fingerprint that is calculated using a hash algorithm. Why this works, how this works, is really non-intuitive, but practically speaking, if you take a block, say an 8 kilobyte block, and you calculate a hash, and you get a fingerprint, whether 16 bytes or 64 bytes, it's been shown that the probability that two different blocks will generate the same fingerprint is lower than the probability that you will have a memory error in your computer. So even though clearly 16 bytes is a lot shorter than 8K bytes, in practice, in nature, when you calculate a hash for a block, the equivalence of the hashes dictates that those original blocks are the same. The fingerprint types that are calculated there are many different names for the algorithms used. A very popular one is called an MD5. This is a Message Digest version 5 that was developed by Ron Rivest. Other algorithms, SHA-1s and SHA-2s, these are the secure hash algorithm, and they have different lengths. The longer the byte length of the fingerprint, the less likely a random collision between hashes. Let me say a few words about the genealogy of deduplication. Ron Rivest, who invented the Message Digest algorithms back in the 1980s, is generally credited with having invented the concept of deduplication. His original research was done on the subject of cryptography, and these message digests were just a side effect of his research. His calculation of message digest made possible the concept of single instant storage, and this is generally dated back to 1989. So he applied a hash to an entire file. Subsequently, people took files and divided them into fixed blocks and applied a hash to each one. That was a fairly straightforward extension. More recently, the variable block algorithm was invented and patented by a company called Rocksoft, based in Australia. This was in 1995, and they described content-defined chunks in their patent. Rocksoft was subsequently acquired by ADIC in March of 2006, and then by Quantum a few months later. The variable block algorithm patent is owned today by Quantum, but similar approaches have been used by companies like EMC with their data domain products. The progressive deduplication algorithm is based on work done by Andrew Tridgell from Australia. He wrote an application that many of you may know called rsync. rsync synchronizes two files across a network. It is effectively a single file deduplication approach that divides each of the files into blocks and uses a two-phase algorithm consisting of a rolling checksum and a hash to determine what the minimum number of blocks are that have to be moved from one location to the other to make those files the same, hence rsync. This same concept of a two-phase equivalence was exploited by Cadena Systems in their 2004 patent around multiple file pools. Cadena Systems was acquired by Arkeia in 2009. In 2009. Arkeia subsequently submitted a series of additional patents around block size optimization, and then Arkeia was acquired by WD last year. So 3 technologies, 3 genealogies. This table summarizes some of the key differences between the different technologies. Remember that single instance storage is deduplication at the file grain. So single instance storage means that if you change any byte in a file or even append a single letter to a file, a single character, that the hash values calculated on that file will be different. So if you append or modify or insert data into the file, single instance storage believes you have an entirely different file. As a result, compression ratios aren't very good, but it is very fast. By comparison, fixed block, because it divides a file into many blocks, and because you can calculate a hash for each of those blocks, if you change the content of the file or add additional blocks, all of the blocks that weren't changed or the blocks that were there originally will still be known to the system, which means that fixed block can tolerate appends and modifies, though it still can't tolerate inserts. So the compression ratios get better, though the speed gets a bit worse. In variable block, we can tolerate appends or modifies, as well as inserts, so the compression ratio gets still better, speed declines again. The objective of progressive deduplication was to take the benefits of variable block in terms of compression, try to improve them still further, while trying to recover the speed performance we saw in fixed block. And you'll see how this works in the coming slides. In addition to understanding the differences between different deduplication implementations and how they've changed over time, it's important to understand the concept of application-aware deduplication. Application-aware deduplication means that the deduplication algorithm, typically the block size, is going to be different based on the type of file. So if you have a file like an MPEG file, any file that's been previously compressed or contains random data, you're going to see the best overall compression multiplier with the largest possible block size. That's because any smaller block is not going to be able to identify any common subblocks, any common content within the file. By comparison, if you are doing deduplication of a PowerPoint file, the optimum compression comes, we know empirically, at a block size of about 1K. As the block size gets bigger, the compression ratios do not improve, and as the block size gets smaller, they fall off as well. Why is this the case? When we first discovered this empirically, we were surprised by the result, but after some thought, the answer became evident. Things are always clear in the rearview mirror. And what we realized was that there are 3 different effects taking place as a function of the block size. As the block size gets bigger, the effectiveness of deduplication, of block deduplication, goes down. If you have a file that is 1 megabyte in size and you're using blocks that are half a megabyte in size, the chances of finding a lot of duplicate blocks are not going to be very good. The performance of very large blocks in dedupe is going to be similar to the performance of single instance storage. By comparison, the smaller the block you use, the better the deduplication rate. If you use a block size that consists of a single character, you're going to see a lot of duplication that can be deduplicated. because the letter A will exist in many, many documents. But the problem of having really small block sizes is the problem of the efficiency of dedupe metadata, shown here in blue. So if you have a lot of really small blocks, even though you're getting great deduplication on those blocks, you're spending a lot of storage keeping track of the pointers to the blocks. So generally, larger block sizes will be more efficient on dedupe, while smaller block sizes will be more efficient on deduplication. So bigger is better for metadata, smaller is better for the dedupe. A final dimension is shown here in green. Local compression will always be better for a larger block size. If you have a block size of 1 byte, no local compression is really practical. Similarly for 2 or 3 or any small blocks. But as the blocks get bigger, the benefit of local compression goes up. So you can see that with these countervailing influences, we end up with a curve like that shown on the previous page. We think that progressive dedupe, the most recently invented dedupe, is the best kind of dedupe. We think it's better because it can be application aware, because it will see all possible block boundaries due to its sliding window. We think it's faster by virtue of the fact that block sizes are fixed and that known data is able to be deduped at the same rate as fixed block dedupe. We think that progressive deduplication's progressive matching algorithms are much superior to the techniques used by variable block dedupe. But let me say that the effectiveness of any dedupe algorithm is very much dependent on the data you have, as is dedupe as a concept in and of itself. So we at WD recommend that you evaluate different deduplication algorithms, different products for deduplicated backup to see which performs best on your own data. Standard benchmarks for deduplication don't really exist, and therefore to accept a standard benchmark as a proxy for your own data doesn't make a lot of sense. Any company can achieve any deduplication rate if they can control the data that goes into the tests. The classic way 5 years ago that companies achieved 100-to-1 compression was to have 200 files that were exactly the same that could be easily deduplicated back down to the volume of just 1 or 2 files. So conduct your own tests. Decide for yourself which dedupe is better, because unfortunately standard tests, standard measures for deduplication efficiency just don't exist today. Okay, let me show you how the dedupe works. Dedupe is really pretty straightforward. We're going to show you first fixed, then variable, then progressive. So fixed block dedupe, as you'll see, takes a window, puts it on the file, calculates a hash for that block, and then moves the window down. So each placement of the window causes a hash to be calculated. Then you look up that hash in the list of known hashes, and if you haven't seen the hash before, it's declared new. This is the first time we've seen this file, so all 4 of these blocks are declared to be new blocks. Now if we look at the file again, this time with data appended to it, and we go through a deduplication process according to the fixed block algorithm, we'll set the window and we'll calculate a hash, and we'll see that the first block is known and the second is known. But when we come to the 4th block, we'll see that there's some new data that causes the hash value to be different. So then we calculate subsequently new blocks. This shows you that fixed block tolerates appends and modifies well. But in the 3rd case, we'll look at how fixed block tolerates inserts. And we'll see that if you insert data into a file, while the first block will be seen and recognized as a known block, all of the subsequent blocks will be perceived as new blocks, either because they're new data or because the same data has been shifted down and the block boundaries have moved, and therefore the hash values are calculated differently. This is the big weakness of fixed block. It can't handle inserts. And many changes made in files one day to the next include inserts, and that's why, for purposes of backup, fixed block deduplication isn't very good, though you might be surprised by the number of vendors that still rely on fixed block dedupe. Variable block dedupe is very different in terms of its algorithm. Variable block dedupe is superior to fixed block because it can tolerate inserts. The way variable block works is a small slit. A small slit is placed on the file, and at every byte offset, a hash is calculated. In variable block, you're looking for a magic number. And when you find that magic number underneath the slit, you declare a block boundary. So if you see a particular sequence of bytes, that's your magic number, that sequence. It's often 0. So if the magic number that you see under the slit is 0, then you declare a block boundary. As for the fixed block dedupe, variable block can handle appends very easily. The slit slides as it did before. It finds a block boundary. It calculates the hash for the block. It'll be a known hash, a known block, and therefore it can proceed. It's only when the sliding slit reaches new data that new data are included in the hash calculation for the block, and the system effectively identifies a new block. This animation that you're seeing is slow. This is not simply the animation. Variable block is a slower process than fixed block because there is more computation that's required to first randomize the file and then to identify block boundaries. But the cost of that slowness is a significant improvement in compression ratio. This is shown in the table on left. So for the variable block column, you can see that appends and inserts are good. You'll see the inserts in just a moment. But the compression ratio, while the compression ratio increases, the speed of the process declines. So here, when we're dealing with the insert of data, the first block will be identified easily. But the magic number that was identified fairly high in the file for the second block is identified only much lower in the file because the whole file has been shifted down. So that second block will be much bigger. It will be a new block, but all the subsequent blocks will be identified where they were because the block boundaries shifted down with the file as new data were inserted. This is why variable block can handle inserts of data as well as appends or modify, and one reason why it's great for purposes of backup. Let me give you a little bit more detail as to how variable block works. It's an interesting process. There are two phases to it. The first phase is to randomize the data. It's important to randomize the data in order to get a smooth distribution of block sizes. So if you randomize the data with a polynomial hash function, you will look at the first n bytes in the file, say the first 8 bytes in the file, and you will calculate a hash based on those n bytes. This hash you're calculating is different than the hash you'll calculate on the blocks after the boundaries are identified. This is just the hash to randomize the data. So you calculate a hash to randomize the data, you create the randomized value at write, and then you continue performing the same process for every subsequent set of 8 bytes seen under that sliding slit. Once you've calculated all of these hashes, your goal is to find block boundaries by looking at the last n bits of these hashes. If you look at the last 4 bits, you'd be looking at the last hexadecimal character in the table at right. If you look at the last 12 bits, you'll be looking at the last 3 characters. And if you're looking at 8 bits, the average size of your block will naturally be 256 bytes, 2 to the 8th. If you're looking at 12 bits, it'll be 2 to the 12th, or 4K. So we're going to look for a magic number that's 12 bits long. That'll be 3 hexadecimal characters. And if we scan those 3 hexadecimal characters at the end, looking for a magic number of 0, we'll find that magic number here once, and that will identify the end, or that will identify a boundary between 2 blocks. That's where a variable block boundary exists. So this is done for the length of the file to divide the file into many blocks, and then subsequently the hash for each block is calculated. This first block will range from bytes 1 to byte 14. The problem with variable block deduplication is that most of the blocks generated by this mechanism are either very small or very large. In fact, half the blocks are smaller than the target block size or larger than twice the target block size. This makes them not very effective for deduplication. By comparison with progressive and fixed block deduplication, every block is the same size. The fact that you have this broad distribution of block sizes in variable block means that there's a lot more calculation that has to be done. It also means that variable block deduplication is not good for being content aware, because you can't take advantage of the fact that different kinds of data are best deduplicated with different block sizes. Now let me show you the example, the animation for progressive deduplication. Progressive had the advantage of knowing how fixed and variable block worked, and could take advantage of what was learned in those previous exercises. So for progressive deduplication, you have a window. This window defines the block. You set the window at the top of a file, and you move it down the file 1 byte at a time. And if you don't find a known block during that process, you declare the block to be a new block. So we've discovered 1 new block, then another new block, and as we continue to scan to the end of the file, if we don't see a block, we'll declare a new block and then a new block again at the end of the file. So progressive dedupe works pretty much the same as fixed or variable for a single file. When you append data to it, it behaves very much like fixed block. The known blocks are identified by simply setting the window and calculating the hash. Notice that there's no sliding when you identify a known block, so that looking at data that's already known, the performance of progressive deduplication is the same as the performance of fixed block deduplication. This is a huge advantage to progressive dedupe. When you insert data, you'll see the same kind of behavior. That is, you'll place the window at the top of the file. It will obviously be the same as it was before, so that block's a known block. When you place the window the second time, it won't recognize the block, and therefore it will slide looking for a block. If it slides the full length of the block and finds nothing, it creates a new block. And then it replaces the window and starts to slide again. But here, it's been able to discover a block that was already known, a block that was identified previously. And once it identifies a known block, once the block boundaries are synchronized, then subsequently it will perform at the speed of fixed block deduplication. This is why progressive, like variable, can handle appends, modifies, and inserts, but also be able to provide better compression ratios than variable block while providing the same kind of performance effectively as fixed block. The reason the performance is largely the same as fixed block is that in a backup environment, 99% of the data you're looking at is data you've seen before, typically. Maybe it's 95%, maybe it's 90%, but the vast majority of data is data you've seen before. So because progressive deduplication can demonstrate the behavior of fixed block deduplication on known data, it enjoys the performance of fixed block dedupe. For those of you who are bold, this flowchart summarizes how progressive matching works. Progressive matching is the technique that's at the heart of progressive dedupe. Progressive matching is the same technique as was used in the rsync application. Progressive matching means there's one algorithm to find likely matches and another algorithm to confirm exact matches. Andrew Tridgell in rsync used checksums for his lightweight algorithm, and then if there was an equivalence of two blocks based on the equivalence of the checksums, he would confirm the equivalence of the blocks using a hash. This is basically the strategy that's used in progressive deduplication, though the lightweight algorithm is more discerning than a checksum. It offers great performance, but it's more discerning than would be a checksum. The objective in progressive matching is to choose a lightweight algorithm that 99.999% of the time gets the answer right using a tiny fraction of the CPU needed to calculate a hash. So what we're trying to avoid are false positives. The fewer false positives, the faster the process. So in summary, the things you need to know about deduplication in order to make good business decisions are relatively few. You have to understand the difference between single instance storage and block grain dedupe. It's better to understand the different kinds of block grain dedupe. It's important to understand what application aware means and how application aware deduplication is achieved. And then it's important to know that the results of deduplication depend hugely on the data that you're seeing. Therefore, using off-the-shelf benchmarks is not today a good strategy for measuring the effectiveness of a deduplication solution. At some point in the future, there may be something like the TPCC, the Transaction Processing Council benchmarks for relational databases, but to date, those standard data sets have not been defined and promulgated. So now let me spend a few minutes, 3 slides, to tell you a little bit about Western Digital. Most of you are probably familiar with Western Digital. Western Digital was founded back in 1970. We are the largest manufacturer of hard drives in the world with over $15 billion in revenue. We have almost 100,000 employees worldwide. We have thousands of active patents and invest heavily in R&D. In order to expand our offerings to SMB companies, we acquired Arkeia software in 2012. The Arkeia product that we acquired is called WD Arkeia. It's been shipping since 1999. WD Arkeia offers backup servers as appliances, but also virtual appliances and software. WD Arkeia's appliances historically have ranged from 2 terabytes to 24 terabytes of capacity. Today we announced a series of new appliances, and as of today the maximum capacity has doubled to 48 terabytes. WD Arkeia is special by virtue of the wide number of platforms that we support, both physical and virtual platforms. We have several key technologies for fast backups. One is our progressive deduplication. Another is multi-flow, allowing the parallel backup of up to 200 clients at the same time. Multi-flow is important because it means that your backups won't be slowed by the slow performance of a single one of your clients. We also support backups to disk, tape, or cloud, and we sell our products exclusively through our VAR and other channel partners. The architecture of our product is a classic network backup architecture. One backup server manages a large number of backup agents, and the backup servers can be administered either by a graphical web user interface or by a command line interface. The command line interface is great for scripting. The backup servers can write to pretty much any storage target, over 600 different kinds of tape drives and tape libraries, but also to disk and to cloud storage. If you have multiple backup servers, you can replicate data from one backup server to another. So if you have a backup server in a remote office and a backup server at the central office, you can replicate backup sets from one to the other as an alternative to using tape. As I mentioned earlier, the backup servers can be deployed as a software application. That's where we got our start, and today we support over 130 different Linux platforms on which our backup servers can be deployed. Our appliances, as of today, range from 2 terabytes to 48 terabytes of disk, and 3 of them include integrated tape drives. Tape is not dead. And then finally, you can deploy our backup servers as virtual appliances on VMware ESX and ESXi hypervisors. Our backup agents backup files and folders. These backup agents, when you purchase an appliance, these backup agents are unlimited. You can use any number of backup agents you want on any set of platforms you want for the fixed price of the backup server. If you have, in addition to files, and again, our file backup agents protect Linux, Windows, Mac, all the Unixes, Novell, and BSD. If you have not just files to back up, but you also have databases or applications or directory servers, we have hot backup agents for all of these. We additionally have specialized agents for VMware and Hyper-V. Our VMware agent permits us to use the vStorage APIs for data protection offered by VMware. We think we offer superlative support for virtualized environments. But also on the backup agent, we provide deduplication, that's source-side deduplication, encryption, as well as bare metal disaster recovery. So we think we have a very rich product, and we invite you to take a look. So, Britton, in the 15 minutes remaining, are there any questions that I can address?
Yeah, we had some great questions come in during the presentation. First question, why would anyone continue to use fixed block dedupe over progressive?
People would continue to use fixed block over variable block for performance reasons. There isn't much of a reason today to use fixed block over progressive dedupe. If you knew that the way your data were being modified from backup to backup was that files were only being appended to, then fixed block deduplication might be adequate. But aside from that, fixed block has largely gone the way of single instance storage.
Okay, next question. Does dedupe make sense for all data?
That's a very good question. Back at the beginning of the presentation on an early slide, I showed that some different kinds of data often had different kinds of deduplication algorithms. So if you had a video, you'd use MPEG. If you had an image, a fixed image, a still image, you might use JPEG. If you have data that are totally random, if the data have been previously compressed, for example, or they have been randomized, or they are themselves random data, nothing you can do will compress them further. There is no algorithm to compress random data. That's why they call it random data. You can't compress it, and to the same extent, you can't deduplicate it. So taking a file full of random data, breaking that data into blocks, looking for common blocks will find you nothing, and trying to compress these individual blocks will give you no compression. So it doesn't make a lot of sense to try to either duplicate or compress random data. And again, random data is data that's random because it's from nature, or it's random because it's already been compressed. Next question.
Next question. Can WD do deduplication across platforms, or does it do dedupe simply for each individual computer?
That's another good question. If you do deduplication on a single computer, it's clear that you're not going to get the benefit of the dimension whereby deduplication can identify a block on one computer that also exists on another computer. In most environments, there's huge overlap between data on multiple computers. So you want what some people call global deduplication. Even though it's called global deduplication because it means it's cross-machine, anything short of global deduplication is just not up to speed, especially for backup, because so often you find, again, the same backup on multiple machines, you have to be able to do dedupe across those machines.
Okay, next question. Doesn't Windows Server already do data deduplication?
Yes, there are versions of Windows Server that do data deduplication. In fact, WD has a product, the WD Sentinel product line, that uses Windows Server and that takes advantage of this deduplication. And the Windows product is a good product. Microsoft has talked a lot about their deduplication product. I think it's variable block deduplication. The challenge of a deduplication solution, though, that is specific to a particular platform type is that you don't get the benefits of seeing common data across machines of different types. So many environments consist of a combination of virtualized machines, VMs, Windows boxes, Linux boxes, maybe Unix or Macintoshes. Ideally, for purposes of backup, you want to be able to deduplicate blocks across all of these computers. That is the best way to get the maximum compression. You also want a single backup solution for all of your machines because you want a consistent strategy applied across all of your machines for data protection. So while the Windows solution is good, it certainly doesn't offer source-side deduplication on non-Windows platforms.
All right. This next question says, this would still be viable for, say, backing up your server alone, wouldn't it?
It would be. It's unusual for businesses to have only a single machine that they want to protect. But if you have only one machine, deduplication will offer value for two reasons. One, because you'll see similar data in multiple files on the same machine, and because data backed up one day to the next will have a huge amount of commonality. You get still better results if you have not just one machine but multiple machines, because then you can take advantage of the commonality of data across multiple machines in a company. But you win either way.
Okay, next question. What about the impact that source-side deduplication will have on the performance of the servers that are being backed up? Don't you want to minimize the impact on these servers whenever possible?
That's the rate of great questions is very high for this webinar. That's an excellent question. That was one of the significant early concerns about doing source-side dedupe. Avamar, a company acquired by EMC, was one of the early companies to deliver source-side dedupe, and they worked very hard for a long time to make the case that the impact on source machines did not outweigh the benefits of reducing the bandwidth on the local area network. It is certainly true that there will be an impact on those machines. You're using a fair amount of CPU and you're using a fair amount of memory to do the dedupe. So it may be the case that in some circumstances you don't want to do source-side dedupe for certain servers. generally the savings you get on bandwidth is worth the additional impact on the source machine. But it might not be the case, and you might have a special case where you don't want to do source side. In that case, you can simply send all your data to the backup server and do the compression there. But it's handy to be able to decide which machines you're going to do the dedupe on and at the source, and which machines are not going to do the dedupe, and those machines that data will be sent to the backup server. And of course, WD Arkeia offers you those options on a per backup, what we call a saved pack basis. Good question, though.
Okay, and one last question. You compared the probability of the same hash being created to having an error with memory on a computer. My question is, what deduplication technology does this exist in?
I'm not sure I understand the question. I did compare the probability of a hash collision to the probability of an error memory. The exposure to hash collisions is an exposure that all deduplication systems carry. This is why very few systems today use key lengths that is hash key lengths that are as short as 16 or 20 bytes. Usually the hash length is much longer, and the longer the hash length, the lower the probability of a collision. But theoretically, there is always that probability. Now, the collision of hash values, even with MD5s, which is the smallest hash that anybody talks about. So even collisions of hashes between two blocks using MD5s has never been recorded in history. It is true that researchers have been able to construct two blocks that are different that have the same hash value with MD5s. That's not been true for SHA-1s or SHA-2s to my knowledge, but it's never been seen in nature, though it has been created in the lab. But it's a factor that to which all deduplication implementations are exposed. Most of the discussion today was about how you decompose a file into blocks. After you've identified your block boundaries, all of the deduplication algorithms calculate the hash for that block in the same way. So all of them are exposed to the same extent. You can minimize your exposure by using longer hash keys, but theoretically you can never make the exposure go away. That's a very good question too. Britton.
Okay, that's it for the Q&A portion of the webinar.
Okay, Britton, thank you for your support, and thank all of you for attending. I'm passionate about deduplication. It's a great technology. It's a huge change to the backup category and has had a huge impact over the last 5 or 10 years, and we expect a huge impact moving forward.
Okay,
Abby?
well, thank you so much, Bill. That was a great presentation, and thank you all who attended today. Just wanted to remind you again that the webinar was recorded, and you will get an email with that link in about a week. So with that, just want to say thanks again to WD and to all of you out there, and we look forward to seeing you on future webinars.